Hi folks, I'm Devanjana and today I'll be mainly discussing about text processing.
Devanjana, so Randhir is asking if we can share the PPT. Is your PPT uploaded on the GitHub?
No, I'll share it after this session.
Okay, I think, yes. So Randhir, we'll share it after this session. Is that okay? Thanks.
Right. So I'll be mainly talking about text processing, classification, and NLP today. And mainly, these are the main topics that we'll be discussing. Uh, most of these things have a lot of derivations and mathematics behind it. So a small disclaimer is we will not be going into the depth of these derivations because it is not possible to cover all of that in 90 minutes. But basically an intuition and an essence of most of these topics we'll try to cover in the next 90 minutes. So in a text classification problem, these are the mainly four things that we do, right? We first pre-process the text, then we encode, then we classify, and then we evaluate. So for this, what are the steps necessary? We'll be mainly talking about all of that in the upcoming slides. So firstly, why do we want to do text processing, or the main motivation behind it, right? So most of you know about this, but just to, uh, talk a bit about it before delving into the technical stuff. So a lot of data is available and most of it is text. And if you look at some of these statistics these days, 18.7 billion text messages, 500 million tweets in every 24 hours, or 40,000 search queries being processed by Google every second. I mean, it's maddening. So given that amount of textual data that we have, processing that manually definitely doesn't make sense. And that is where, the path for NLP got paved, right? And we basically want to make the computer understand textual records, process them, and, discover interesting insights, do certain tasks, so that firstly it's faster and also it is cheaper, requires less manpower. So this is just a recent article that I came across in Hindu, and I thought I'll share just to support the fact that uh, the rate at which data is booming these days, which makes NLP so much more relevant to know, a skill set to have for all of us. So mainly the thing that I was talking about in the last slide, and some popular NLP tasks that I'm sure most of you have come across: text classification, dialogue generation, text summarization, machine translation. So for machine translation, I'm sure most of you have used Google Translate. Text summarization, I'm not sure if they still use it, but some of these news apps, they have these 60-word summaries that they present to use text summarization models at the backend. Dialogue generation, classic chatbots that you have, Siri, Bing, all of these have uh, Bixby, all of these have dialogue generation models running in the backend. And text classification, well, a lot of use cases, right? You have sentiment analysis on movie reviews, you have, classifying fake from non-fake uh, news articles. So just to give a few examples of what some classic NLP tasks are like. So we'll be talking about text pre-processing now, and these are the main steps that classically we follow to process text. So first we do noise removal, which mainly includes removing white spaces, removing HTML tags, converting accented characters, removing special characters, um, and removing stop words. Then we have normalization, which is low casing characters, expanding contractions, which would basically mean if you have abbreviations, we want to expand them. Then converting numeric numbers, stemming, lemmatization. We have tokenization, and then we have building the vocabulary, removing duplicate words, and finally vectorization, that is we embed the text using word embeddings. It could be TF-IDF, word to vec, or many other embeddings at others. So with that, we get our processed text. And before we move further, we'll move to the hands-on session and do some of the text pre-processing stuff, because some of the steps do take some time. So we'll start that, we'll keep that running, and we'll go on with the presentation once these things keeps running, right? So I'm not going over the steps, the initial steps. So Ranjan has already shown, right, how to install the Conda environment and all. So I'm directly moving to the notebook. My screen is visible to everybody, right?
Yes.
Okay. And I will be going through each of these blocks. Wherever you face difficulty, please, you can, unmute yourselves and say, or write in the chat, whichever you're more comfortable with, right? So these are all the packages that we will be requiring here. So first we will download them. So let me maybe refresh my kernel. Run it with all of it. This time. Okay. So first we will be downloading all of these packages. We will be using the news category dataset. So I'd mentioned in the Git repo earlier to download the dataset and place it in this folder. I hope all of you have done it. In case not, you need to place it in this particular folder. So once you clone this under supervised ML NLP, you need to place the JSON file in order to run this. So we read the data. We will read, so it's a JSON file. We will read it. I'm just printing a snapshot of the data to understand what it looks like. So we have the category. We'll be mainly using the headline. We'll be categorizing the headlines into, there are 20 categories, but we will be using 3. So out of the 20 categories, we'll be looking at entertainment, politics, and tech. So that is what so if I'm not sure if all of you are familiar with most of these packages, but pandas is a very, I will definitely encourage the usage of pandas. Pandas is a very handy technology or tool. It could be used to process data, have it in a tabular format, moving from one version to other, making plots. It's very easy with pandas. So definitely encourage the usage of panda. So we have around 50,000 data points. So a bit of data analysis, we will be looking at, so we just plot it. So the data is definitely imbalanced, and we can see that, the amount of tech data is very low compared to politics and entertainment. So that effect of imbalanced data, you'll be able to see in the classification notebook. But just a thing to have in mind, these distributions help in analyzing output from, classification tasks. So whichever NLP task you run, it definitely helps to, analyze the results later. So data set we will now pre-process. So first we will remove non-English sentences. So this is the one which takes a bit of time. So we'll come to this at the end. We will keep this running and move to the next slides. So before that, we'll look at these, right? So we'll just take a sentence and, look at the different pre-processing steps. So if we have this text, drag run quickly to the stumps. We will use regex, another powerful tool, to remove punctuations and special characters. Okay, sorry, I did not run this. Right. So we do that, you see. It has been lowercased, and we have removed extra characters. Then we tokenize. So we're using NLTK word tokenize over here to tokenize the text. NLTK, again, another powerful technology that I will recommend. Very, very popularly used in the NLP community. Then we will remove stop words. Stop words are basically the words which are, very commonly found in any language. So over here, we're looking at English stop words. It can be different for other languages as well, which usually do not, impart much information. So I, me, my, myself, over here, you can see we are basically, again, downloading stop words from NLTK. So these are some of these stop words that are there, right? You can see articles, conjunctions, very popularly, very common words are basically the stop words. So we remove stop words from the text. Then we do stemming and lemmatization. So stemming and lemmatization both basically have the same goal. They basically, change the word to its root form. So for example, quickly, it will remove the last ly and bring it to its root form. But the main difference between stemming and lemmatization would be that stemming uses some heuristics to basically remove the inflections and last inflections being the lys and the llys basically. And lemmatization uses and Porter stemmer is one of the is a very popularly used stemming technology. And lemmatization actually involves morphological analysis of the words and is a bit more sophisticated. So lemmatization is more popularly used to bring the words to its root forms. So we will do that. We will do stemming and lemmatization both. And for lemmatization, we are using WordNet from NLTK. So all of this has been put into a function. And to do this, so basically, just to show it one by one, I've taken a text and I'm showing it here. But otherwise, everything is in one function. And if you run it on the entire text now, it will give you the clean text. Okay, no, sorry, we can't run this because we will need to do this. So we will keep this running. This takes a bit of time. Yeah, we need to remove, so there are certain non-English sentences in this data set. So we will remove that. This takes a bit of time. So we will let these two run and we will continue with our session. So I'm hoping everybody could follow because these are very simple steps. I'm hoping everybody could follow through these steps. In case you have problems, do let me know on the chat. Pratiti or any other organizer can actually, read them out. So I'll let this run and move on to the session. Right. So right now, after this, we'll be moving to text representation. So text representation has evolved over the years, right? So first we had to represent words, we had frequency-based embeddings. Then a bit more sophisticated embeddings came with the use of language models. Then subword embeddings, and then finally we had contextual embeddings. So we'll go one by one quickly. And so just for people who are not familiar with word embeddings, word embedding is basically, so you need a numerical representation of the text, right, to feed into the machine. So that numerical representation that we learn is known as the word embedding. And when we are learning these representations, usually the words which have similar meaning have similar representations. So and these vectors all have a fixed size vocabulary. So these vectors have a fixed vector size as well. So the first embedding that we'll be looking at are one-hot encodings. And over here, we'll look at that through term document instance matrices. So over here, the example that we'll be looking at is we have different, Shakespeare, classic Shakespeare plays. So Antony and Cleopatra, Julius Caesar, Tempest, Hamlet, Othello, and Macbeth. And some of the words we have that appear in these plays. So if Anthony appears in Antony and Cleopatra, we have put 1. If Anthony doesn't appear in one of the plays, for example, in Tempest, it doesn't appear, so we have put 0. So like that, matrix has been formed. And for this document, this would be the binary vector for the document Julius Caesar. So this was the basic form of embedding. A bit more advanced from that was the count matrix. So instead of putting just ones and zeros, now we will put the frequency of the terms. So if Anthony appeared 157 times in Anthony and Cleopatra, that has been documented. If Caesar appeared 227 times in Julius Caesar. So like that, we have the counts, and similarly, we get the count vector of the document. So with that, now the problem with this is the main idea of word embedding, we want to encode, the grammatical structure, the meanings of the words, the sentences. So when we want to do that, binary vectors or count vectors do not encode that very nicely. And what we see is when we look at these term frequencies just in itself cannot show the importance of a word. So what we can see is a lot of times, for example, if you look at some of these stop words, right? Some words which appear repeatedly do not impart important information, whereas some of the words which appear rarely in the meeting, rarely in the documents, they actually impart important information. So to encode that information, TF-IDF was born, and that was the intuition behind TF-IDF. And this is how TF-IDF is calculated, right? So TF would be the term frequency, and that is the number of times the term occurs in the document divided by the total number of words in the document. IDF is the inverse document frequency, and we basically find the total number of documents divided by the number of documents containing that word, and we take a log of that. And then TF-IDF would be a multiplication of these two values. Now, this is the basic version. If you go into the literature, you'll find a lot of different variations. So there are some smooth out versions of these, some log damp variations of these. So there are different variations, but this is the the crux of TF-IDF that is there. So the best way to understand TF-IDF would be to look at some examples. So we have these. We'll consider these 3 sentences as 3 documents, and okay, right. So these, if we just have a look at this matrix. So we'll first calculate the term frequencies, right? Sorry. We'll calculate the term frequencies of document 1. So the number of times the term occurs in the document. So going occurs once, and there are 6 words. So likewise, we get 0.16. Similarly, so all of the words appear once. So like that, we have 0.16. Similarly, for document 2. And in document 3, there are 8 words. So, and each of the words appear once. So we get 1/8, so 0.12. We haven't shown for all the words, but for some of the words we are showing in this slide. And so that is how we calculate the TF. Then we calculate the IDF. So IDF would be, the total number of documents and the number of documents containing the word. So total number of documents is 3, and then the number of documents containing the word going is all 3 contain going. So 3/3. I is there in document 2 and document 3. So 3/2. Similarly, is just there in first document. So 3/1. So we calculate the log values, and likewise, we then calculate the TF-IDF. So we will multiply 0.16 with 0.47, and we'll get this value. And 0.16 with 0.47 with points, which will give us 0.752 again. So like this, we calculate, the TF-IDF values again, 0.16 with 0.17, 0.16, yeah, we will get this. So we calculate the TF-IDF vectors. So if we have, I'll probably give a minute or two if we can calculate, you know, the TF-IDF values for just two, not for both the rows, just for uh, two if you can calculate, and share it in the comments. You don't need any fancy calculator for this. You just sorry, I stopped sharing, I think. Sorry, guys. Yeah, so I see Diwakar has shared the term frequency for D1. Can you calculate IDF and the TF-IDF? So uh, 2 appears once in the first document, and there are 6 words, right? So the term frequency will be 1/6. So I think Diwakar has mentioned that, which is correct. Right. Yeah, I can see Sulfuraz is also mentioned. Yeah, that is the term frequency. Can we have the IDFs? So for the right, so I cannot wait any further actually because I have more content to cover. So for the interest of time, I will show the values. Right, so it is 3/2. Log IDF is log 3/2. Correct. So 1/6, log 3/2, and you multiply them and you get TF-IDF. Similarly, for today also, it will be same, right? So this now will be the TF-IDF vector for document 1, right? So we'll move on to the next representation that we have, and that is word-to-vec. Now, word-to-vec is a more sophisticated and much stronger representation that, you know, with the advent of language models was born. So language, so for people who don't know what language models is, in a very you know, easy way, I'll say, language models are basically those algorithms which will help you predict the nth word given the n-1 words, right? So if you've seen n-1 words, you'll be able to predict the nth word. So using that, word2vec was one. So there are, so you can see the idea, right? We have a text, we tokenize the text, we have a list of words, and we have a fixed vocabulary. And then for each of the words in word2vec, a context is defined. So for example, if you look at this picture, right? Say if we take the word into in consideration, and we define a context window of 2, then we will look at the 2 words before it and 2 words after it. So and then we will calculate these probabilities for each of these. So we will calculate the probability of turning if into is given, the probability of problems if into is given, then the probability of banking given into is given, and probability of crisis given into is given. So like this, we calculate the probabilities, and we have two variations of this basically. We have a continuous bag of words model where given the middle word, we will, guess the surrounding words or the context words. And the other one is the skip gram model. That is, given the surrounding words, we will, sorry, I think I said the opposite. Yeah. So given the context words, we will, in CBOW, given the context words, we predict the, middle word. So over here, if problems turning banking crisis is given, we need to predict into. So that will be CBOW. And this is an example of skipgram. So given into, we are predicting turning problems banking crisis. And to learn this, we basically optimize this loss function. So again, so given this is a loss function for a skipgram model. So given the central word, and where if there are t words in the document, if there are t words in the document, we will go through each of these words and we will look at a context window of size m. So for each of these central words, we look at the words within that context window and we will try to predict it. We'll take a log probability of that and we'll want to minimize the summation of that. So this is, we'll go get more into the loss functions later, but this is basically what word2vec is and how word2vec is trained. So I think there is a question. Is RNN used for word2vec? No, not RNN. It's a simple, neural network model that is there for word2vec. So after word2vec, there were more, the next one was glove, and then we had, subword embeddings like fast text, after which came contextual embeddings. So I'll tell you how contextual embeddings help. So for example, if you take the sentence, after collecting money from the state bank, I went for a walk by the river bank. Now there are two banks in this sentence, and both the banks, if I encode it with word2vec, will have the same representation. However, if we embed it using, but they're contextually very different, right? I mean, any us human beings can understand, okay, one is talking about bank where money is stored and another is a river bank. So these representations should also be different. So to encode that context and to have even more powerful semantic or, meaning representations, contextual embeddings were born. And so after that unfit came, then we had Elmo. So this is an architecture of Elmo where we have the bilateral model and, it is basically a bilateral model where we're learning to predict words from forward and we're learning to predict words from the back, from both the directions, and have a function to concatenate these two representations. And even more powerful representations are using the transformers. So BERT, GPT, they all use transformers. Transformers, but these are all, transformers is definitely outside scope for today, but just to, give a flavor of the state of the art embeddings that are there out there. BERT also has various versions now, but these are basically the context, and contextual embeddings are the most powerful embeddings that are being used these days. So these are basically the embeddings that are there and are used to encode text. So we'll go back to our, hands-on. By now, yes, by now it should have trained. So we have removed the, so earlier we had 50,000 data points. Now you see after removing non-English text, we have 48,000 data points. And we will clean the text by calling this function. Right. After which we'll split the data set for the next one, right? For classification, we are basically processing the text and keeping it ready for the next task. So we will split that corpus into 70-30 ratio. So 70% of the corpus we'll keep for training and 30 for testing. Hence, you mentioned this here. So that gives us this split. We have the corpus. And we will save it using pickle files, right? So now we will look into the text representation. So you were talking about count vectors. So count vectors, we can just to have a flavor of how count vectors look like, using sklearn count vectorizer to obtain the count vectors, and we will. This is how basically it produces a sparse matrix, and the vocabulary in the vocabulary you can see each of these words is mapped to an index. Similarly, we have TF-IDF embeddings. So same process, and we have the sparse matrix. So we will plot this sparse matrix. Just give it a second. So you can see, right, like embeddings with, most of them are 0, and just the black ones are basically the non-zero values. So for the entire corpus, the embeddings are very sparse. So sparse vectors are usually, not that powerful, but that is why we have the advent of these other embeddings that came into the picture, right? So we will look into word2vec. So for word2vec, we'll be using GenSim, another popularly used package in NLP. So the word2vec that we are downloading here is trained on Google News Corpus. It has around, I think, 3 billion words, if I'm not mistaken. So once that is downloaded, these are basically pre-trained word vectors that we're downloading. We can, look at some words which are similar, and the scores that you see over here are basically cosine similarity scores. That is given a way to measure the similarity between two word representations. So we see with cat, cats, dog, kitten, so all related words you can see, right, are present. Similarly, with car, you can see vehicle, cars, SUV, minivan, truck. These are the words which are similar. So that gives us a sense that the word vectors were trained correctly. So if you're here we're using pre-trained word vectors, but usually when we are training models, we train our own word2vec vectors, or fast text vectors, or whichever vectors we fine tune or we train ourselves. This is a easy way to evaluate your word vectors to see whether the vectors that you've trained are correct or not, because if they have been trained correctly, then they should map to similar words, right? So just to give an intuition, so these vectors have size 300, and this is how the vector looks like, as I was saying. So we will, so I have written a function to embed the corpus, and if you want to, embed the entire corpus and train the classifiers later with word2vec, you can do that, but it takes a lot of time. So for the interest of time, I have commented it out, but it is there. You can run it. It takes a lot of time. So I'm not doing it, but I had plotted the train embeddings. So don't run this, because since you don't have the train embeddings, you will not be able to run. So I just have kept this to show the plot. So if you compare it with the sparse matrix here, this is a much more dense matrix that we have for word2vec, right? Finally, to use the state-of-the-art embeddings we have bought, so we need to basically use transformers package. So when you were installing, if you've gone through the requirements.txt, you must have seen you've installed transformers package. So from transformers, we are basically, I go up, you see, from transformers, we're basically importing BERT tokenizer and BERT model and using that to encode your text. So for each of these, so BERT has its own tokenizer. You can read more about it. Their tokenization strategy is different from what we do white space tokenization, but they do subword level of tokenization, which you can have a look at. So they you tokenize and you download the model over here, and you can look at the model config. And if you run this, so we've taken a text over here because each of these embeddings are 768 dimensions. So storing these embeddings or encoding the entire corpus and storing that would take a huge amount. So if you encode this and if you just look at the tokenized inputs, you will see this is the tokenized output that you have, and the input IDs. If you map the input ID, so in input IDs you will see, so here there is 1, 2, 3, 4, 5, 6, and here you'll have 8. So you might wonder that why 8. So BERT adds 2 special tokens, CLS and separation token. So CLS token is a very important token that basically is also called the classification head. So it contains the information for the entire sentence. And separation token is basically marks the end of the sentence. And if you run this, you will be getting your the last hidden state basically. So there are 12 layers in BERT. So for that, the last hidden state. So there are 8 words. So for 8 words, each of size 768, you get the vectors. So these are mainly, if I run this, it doesn't take time. This might take some time. Right. So this is basically, an overview of what embeddings are, how they look like, and how you can use it in your projects. So going back to our session, now we'll move forward with the next segment, and that is, so now we have processed the text, we have encoded the text, and now we can finally classify it. So we will look at some classification strategies now. So for machine learning, we have classically we have supervised and unsupervised, two main broad regimes under machine learning: supervised and unsupervised algorithms. And in supervised, we have classification and regression. We have classification, regression, and in unsupervised, we have clustering, and we have dimensional reduction, topic modeling. So unsupervised will be covered in the sessions tomorrow. Today we'll be mainly looking at supervised and classification problems. So for classification, some popular algorithms are logistic regression, support vector machines, neural network decision trees, random forest. For regression, some popular algorithms would be linear regression, multivariate linear regression. Clustering, we have k-means, we have hierarchical, we have clustering, we have dbScan. For dimensional reduction, PCA is very popularly used, and for topic modeling, LDA is very popularly used. So in supervised classification, the main difference between supervised and unsupervised classification, in supervised classification, we have a labeled data set. So we have a manually labeled data set, which we, which we use to train our algorithms, but in unsupervised, there is no labeled data set. So that is where the main difference lies. And so when we have the training set, when we're learning in the learning algorithm, we're basically trying to learn a hypothesis function, which we will be using. This term we'll be using a lot in the later slides. So this So it is hypothesis function is basically a mapping function which we need to learn so that it can learn a good mapping between the input x and the output y, such that when it is predicting the y, it is uh, as close to the original y as possible, or as close to the original output as possible. I mean, ideally, it should be exactly the same, but practically that doesn't happen. There is some amount of error, but that is how the hypothesis function is defined. So here we have a hypothesis function that we have defined. It should remind you of, the equation of a straight line. And this is basically the hypothesis function for for linear regression problem. And over here, the theta 0 and theta 1 that you see. So theta 0 and theta 1 are basically learnable parameters, uh, or parameters or weights that we learn, and x is the input. So supervised classification can be of two types, multi-class and multi-label. And I'll quickly take an example to explain this, right? So say you have 5 sentences and you have 5 classes. And in multi-class, what happens is each sentence can map to any one of the 5 classes in the sentence classification task. So that would be your multi-class classification. But in multi-label, each sentence can map to more than one of the classes from the 5 set classes that are there. So there are 5 classes. One sentence can map to 1 class or 2 class or 3 class or 4 class or all of the 5 classes. So that is multi-label classification. So before we look at some of the supervised classifiers, these are some basic terms that we need to be aware of. So first is the loss function. So in loss function, the algorithm, so we have the output, right? Y is the output, and we are using a hypothesis function to get an output out of the training algorithm. So the difference between the predicted output and the golden output, or the label that is there, that is your error. And that is how we want to minimize that error as much as possible. So that we do using a loss function, right? So there are basically main two categories, the various different types of loss functions. But the two main categories of loss functions are mean squared error loss, that is, you can see, right? So h theta xi is the hypothesis from which we are getting the predicted output. Yi is our, the label that is there. We take a difference, that is the error, we square it, and we take a average of it, m being the total number of data points that are there. So one question could be that why are we adding this to? So if this is mainly added for convenience, so we will not get into the derivations, but for when we are doing gradient descent, when we are basically calculating a minimum over this during we're taking a derivative basically in gradient descent. So this too actually helps that. So that is for the convenience of computations, this has been added. And there is cross entropy or log loss. That is another type of loss. So that is, so again, we have the predicted output from the hypothesis function h theta xi, and we're taking a log of it, multiplying it with the label. And for each of the m points, we are doing that, and we're taking a negative summation of that. So these are the two main loss functions. And in general, mean square error loss is mainly used for regression problems, and cross entropy or log loss is used for classification problems. So we have, the next is, optimization algorithms. So mainly we're talking about gradient descent. This again has a lot of derivation behind it, so I will not be getting into the math. I don't want to, have an overload of information in this one session. But just to give an idea, so we have the hypothesis function. Uh, in the hypothesis, we'll just go back, right? So we have the hypothesis function here. There are parameters, and so hypothesis function will give us an output, which is the predicted output. So we have the loss function where we are adjusting the errors. We get the error from there. And then we also need to estimate the parameters. So gradient descent basically gives us a way to calculate or estimate these parameters or weights in the hypothesis function. And gradient descent is one algorithm. There are various different algorithms. And if you look at this, basically, so in what gradient descent, what we do is we take a derivative of the loss function, and our objective is to have the global cost minimum. So we want the weight for which the loss function there is minimum amount of error, right? And that is, so iteratively we keep on updating. So this is the equation for updating weights, and iteratively we keep doing that until unless we reach the global minimum. So this point of minima is called the global minima. And until unless we reach this, we do gradient descent. And the steps, the how large a step we should take towards the descent is known as learning rate. So the parameter that will control how large a step we should take in the direction of the descent is called learning rate, and that is denoted by alpha. So if the learning rate is very high, then there will be so it will not be able to converge. It will overshoot, like it will go this way, that way. And if the alpha is very low, then it will converge, but it will be very slow. So we have looked at the basic terminology. So we'll be looking at the first classifier, that is logistic regression. So for logistic regression, the hypothesis function that we were looking at all this while was for linear regression, right? And linear regression is basically modeling a relationship between an output, numerical output y, and there can be the x can have one or more explanatory features. Now, y in this for linear regression is continuous, so that is where regression comes into play. But if the output is discrete or categorical, that is where we use logistic regression. So as we have denoted here, right? So whether a person voted or did not vote, or whether the tumor is malignant or not, these kind of classifications we will do not via linear regression, but by supervised classifiers like logistic regression. So logistic regression, this is the hypothesis function. So for every classifier, we will look at the hypothesis and the loss function. These are the main two things that we want to look at. So the hypothesis function is as such. So it is passed through an active a function which is known as sigmoid function, and this is how it looks like. So it basically helps to form a decision. So say in a binary classification problem, it helps to find like this through this hypothesis function, it helps to form a decision boundary between the two classes. Now, if it's a it can in linear regression it would be a straight line, but in logistic regression, if we want to, this will give us a non-linear decision boundary using this sigmoid function. So that helps us process these categorical values. So then we have this is how the loss function looks like. So we just looked at cross entropy. Now the cross entropy loss function, if you simplify it for binary classification, so this is how it will look like for logistic regression. So it is basically the same. If I just go back, this is the same formula as it is here, but this is how the loss function would look like for logistic regression. So the next classifier that we will be looking at is neural networks. So neural networks can handle more complex hypothesis functions. Can for more complex tasks we can use neural networks. Now neural networks are basically, these networks were basically designed to mimic the human brain. So, and in human brain we have neurons. So each of these in a neural network, like the way our body works. Like each of the neurons are connected through dendrites and synapses. So similarly, over here we have layers of neurons, and each of these layers are connected and updated with weights. So, and each of these layers consist of computational nodes, which we call neurons over here, right? So if I explain via this image here, so x1, x2 till xn will be the inputs, and we have the weights. So we will update through the weights, and we have a bias, and the hypothesis function would look something like this, right? There should be a right over here. So theta 0 x0 plus theta 1 x1 plus theta n xn. So theta is basically the weights. So over here, each of these, so x1 will be multiplied with w1, x2 will be multiplied with w2, xn will be multiplied with wn, and a bias will be added. It will all be summed, and it will be passed through so it is a weighted sum of the inputs along with the bias. It is passed to an activation function, which will give us the output. Now, in between, there can be, this is like a one layer neural network. There can be several layers. So in neural network, an activation function is very important. And it is basically, a transfer function. So over here also, you see we have a weighted sum. And this function will basically transfer this, map this value to the output. And so over here, this is a one layer neural network. If there are more layers, it basically decides whether the next neuron will be fired or not, or whether the next neuron will be activated or not. So yeah, that is exactly right. The mathematical gate between the input feeding the current neuron and its output going to the next layer, and it decides whether the next neuron will be activated or not. And there are different kinds of activation functions. Just three I have mentioned here, but there are a variety of activation functions nowadays. But these are the three classical activation functions. Sigmoid we have already seen. Then there is tanh, and there is ReLU. So each of these actually came into existence because of the disadvantages of the prior. So in the interest of time, I will not delve into that, but I will definitely encourage reading up on that, like why tanh came into the picture, or why ReLU was proposed as an activation function. And there is another called leaky ReLU. So on, every activation function was solving some problem that was not solved before. So you can have a look at it. So neural network training is in itself a very big, topic, and just like very, very basic scratching the surface over here. So both this in itself has a lot of derivations. Forward propagation, back propagation has a lot of derivation. So we'll be not be getting into it. So just an intuition, right? How neural networks are trained. So we randomly initialize the weights first. Then we have this hypothesis function, right? So theta 0, theta 1, these are the weights. So with each weight, we are multiplying the inputs. And then then we have the bias term. And then we implement the forward propagation. So forward propagation would be the weighted sum, and then it is passed through an activation function. So that would be the forward propagation. And through each layer that would pass, ultimately it will come to the output will be rendered. So reference would be the the label that we have, and output is the predicted output. We calculate the error using the loss function that we have, and then once the error is calculated, we back propagate it, or we send a signal basically to the network that this is the error and this is how the weights need to be adjusted to learn the outputs better. So when we are learning the back propagating the weights, we are basically adjusting the weights in the neural network, and this is done iteratively until unless the error is stable, or we want to run for a particular number of iterations. So the word that is used a lot in this case is epochs. So probably people who have some hands-on experience in training neural networks would know that. So you set a number of epochs and you train your neural networks for that particular number of epochs, or the error is not, there's not much variation in the errors. So this is mainly, what we have for the supervised classifiers. Now, if we look at, so we have classified. Now, if we want to look at, how we want to evaluate the classifiers, right? So we have four things that we definitely need to know: true positive, true negative, false positive, false negative. So again, I will take the help of an example so that it is easy to understand. So again, if we take the example of tumor being malignant or not, or tumor being cancerous or not, and let the positive class be, it being cancerous or it being malignant, and let the negative class being it being not malignant, non-malignant, or non-cancerous. So if the model, if if a data point which is cancerous, corresponds to the cancer class and has been predicted as cancerous, then that is true positive. If uh, if it is non-cancerous and has been predicted as non-cancerous, then it is true negative. If it is uh, non-cancerous but is predicted as cancerous, then it would be false positive. And if it is cancerous but predicted as non-cancerous, then it would be false negative. So that is exactly what it is saying, right? If an outcome where the model correctly predicts the positive class, then that is true positive. Outcome where the model correctly predicts a negative class would be true negative. Outcome where the model incorrectly predicts the positive class would be false positive, and outcome where the model incorrectly predicts negative class would be false negative. So using this, we can form a confusion matrix, which we'll be talking about in the next slide. And this is basically, we calculate the precision recall F score using these values. So precision would be, the proportion of positive identifications which were correct. So that would be true positive by true positive plus false positive. Recall would be out of the actual positive, how many were identified correctly. So that would be the recall. So that is, sorry, there would be a division sign here. So true positive by true positive plus false negative. F1 score is basically the harmonic mean of precision and recall. So that is, 2 into precision into recall by precision plus recall. And accuracy is the fraction of predictions that the model has predicted correctly. So the total number of correct predictions divided by total number of predictions. And using true positive, true negative, this is how we can calculate it. So I was talking about confusion matrix, right? So confusion matrix is a very important tool, visualization method that is utilized very rampantly during classification or any other NLP tasks, a lot of NLP tasks. And it basically helps us to understand, where the model is getting confused, between which two classes the model is getting confused. So having a confusion matrix handy during classification tasks is very helpful. So these are some examples of, a confusion matrix. And this is how, so you have the predicted condition of the actual condition, and you, populate it with the true positive, false negative values. Another important metric which can be utilized for evaluation of classification would be the ROC curve, or also, so basically it's an abbreviation for receiver operating characteristic curve. So it basically plots two parameters, that is the true positive rate and the false positive rate. So true positive rate is basically recall, also known as specificity. So it tells us what proportion of the negative class is classified correctly. So both these true positive rate and false positive rate, they look at the negative class. So yeah, what proportion negative class gets correctly classified. So this is, so true positive by true positive plus false negative. And then we have the false positive rate, which also known as sensitivity. So it tells us what proportion of the negative class got incorrectly classified, which is also 1 minus specificity and false positive by false positive plus true negative. So what is desirable is we want a higher uh, true positive rate. Sorry, this should be positive rate. A higher true positive rate and a lower false positive rate. And the area under this curve is basically known as the, AUC, or the area under the curve, is a measure that also helps us, I understand how well the classifier has been trained. So if we have a high AUC value, it means that, the model is good at distinguishing between the positive and the negative classes. So these are mainly used for binary classification tasks, but it can also be, extended to multi-class classification problems. So with that, we will now move on to the hands-on session. So we will look at the next. So we have two notebooks. One is for text pre-processing, and the other one is called text classification. So again, we will, download these packages. Let me restart the kernel. Right. So this is where we download the packages. We load the data. So we had already, split the data into X train and Y test in the previous notebook. Then we have a function for, so we've written a function for evaluation, but I have separated it out so we can go through it step by step. So first we look at logistic regression. So both logistic regression, neural network, these two classifiers we've mainly looked at in today's tutorial. And we'll be using the sklearn models. We'll be sklearn, again, a very popular tool or package that is used very rampantly in the NLP community. And for these classifiers, machine learning classifiers, sklearn is what that is most commonly used. So we will run logistic regression. So for logistic, we will first vectorize using TF-IDF vectors. Then we will call the logistic regression model. So random state, these are basically different parameters that I will urge you to look at in the documentation. So random state basically here refers to the, basically sets a seed for, so that the result doesn't change over time, the number of iterations for which this is going to run, and penalties basically. So regularization is something that Suranjana was talking about in her previous lecture, and there are two kinds of regularization, L1 and L2. So here we are giving L2 regularization. So then we will be testing the model. So we are generating the predictions as well as the prediction probabilities through two different functions. So you can do that. And prediction probabilities are basically, the probability with which the model is predicting the particular output. So that probability we can, get through this function. So if you want to evaluate, if you want to run, so for entertainment, politics, we see the scores are both, but for tech, you can see it is just a 1% F1 score. So if you remember, when we were doing the text analysis, we had seen that, the data was highly biased. So that effect we can see over here. Since the data is biased, the score, the number of, firstly, the number of data points that were there for the model to learn about tech was very less. Also, the other data points for the other classes were very high compared to it. So a bias has been created in the model. So if we run the confusion matrix, we can see that, right? So entertainment, politics, they're getting correctly classified mostly. But for tech, most of it is getting, is getting confused with politics and followed by entertainment. So that is, this is how the confusion matrix helps us, and we can, adjust accordingly. So we can run the, so this is the score for area under curve, and we can plot the ROC over here, right? So we are plotting, the ROC for entertainment, politics, and tech. So as I was mentioning, right, ROC usually is done for binary classification problems. So here we are basically converting a multi-class classification problem into uh, several three binary classification tasks. So when we are plotting the AU's ROC curve for, say, entertainment, so all the other labels corresponding to politics and tech will be 0, and the ones corresponding to entertainment will be 1. So like that, we are doing. Another interesting you know curve to look at would be the precision recall curve. So we run that and we look at the different thresholds at which the precision and recall scores perform the best. So ultimately so I just broke it down to show you separately one by one, but otherwise we have an entire function. It is always good to have modularized code. So if we run this one function, it should give us all the results in one place. So we will do the same thing for neural networks. So we will run neural networks, and we have the NLP classifiers, right? So we again, for NLP classifier, we have we are using ReLU activation function. We are setting alpha, that is the learning rate, to 0.0001. And the learning rate, we are not, so there are different other algorithms where the learning rate can be adaptive, but here the learning rate is constant. And instead of stochastic gradient descent, the optimization algorithm being used here is ADAM. So feel free to, it's always a good idea to read up about the models that you're using, the hyperparameters there, and what each hyperparameter means and refers to. So we will fit the model here. This will take some time. So once we fit the model, we will be testing it, and again finding the predicted, the y-pred and the prediction probabilities, and then we'll be finally calling the evaluate function. So as I was mentioning, right, so even in the slides, neural network is a much more powerful algorithm than logistic regression, and can handle more complex hypothesis functions. So for this particular task, a more complex hypothesis function was required. So you see, even though the data is unbalanced, the results for tech have improved by a large margin, very large margin. But still, if you look at the confusion matrix, most of the confusion is happening in the politics domain, right, for tech. And we are also printing the ROC and the precision recall curves. So this will take some time, but if we run all these steps, we will be getting these values. So this is mainly what I had in mind that I wanted to share. While this is happening, I also want to walk you through some of our NLP notebooks that we use at IBM. So this is a public
So Debanjana, sorry to interrupt. We'll cover this tomorrow. So
Okay.
we can skip it today.
Okay, sure. Fine. So, right then, more or less, if there are any questions, I'll be very happy to take them. Any part you did not understand, or you know. Also, I would definitely, so here we just scratched the surface, like it was a very, very high level overview. I will definitely recommend, going through CS 224N. That's a Stanford lecture series that I always find very helpful, and always recommend others to follow as well for, having an in-depth understanding of NLP techniques and classical NLP algorithms. Also, Andrew NG lectures are good, apart from a lot of blogs and that are available these days. But yeah, these two are mainly very important repositories and resources that can be tapped into. And for hands-on, if you are very new to NLP, definitely look at a lot of Kaggle, challenges go on. Best thing is to start from Kaggle challenges and then slowly, get your hands dirty, because from personal experience, I can tell you, just learning from theory, just learning from books never help. So hands-on is basically the best way to learn all this, be it ML, be it AI, NLP, any of the courses.
So Debanjana, on that note, if since we are here, maybe 5 more minutes, if anybody else is still facing issues with the installations or running the notebooks, we can discuss now. We can see if we can do it in the next 5 to 10 minutes.
Yeah, sure.
I think there was one question from Dibakar. How many layers in the NN classifier? How many hidden layers?
In which classifier? Oh, in for the word to where?
Dibakar, can you speak up? Yeah.
Oh, okay. Over here. So we are basically using the default value over here in the MLP. So it's one, I believe. I need to check. I'm not sure, but we're basically using the default value over here.
Yeah, there is only one
One
layer right now. Yeah, it's a basic multi-layer perceptron.
Yeah.
But I'm sure there is an argument that you can use to specify how many layers do you want.
Yeah, I'm sure there will be. I need to check that. For simple tutorial purposes, I did not add, but yeah, surely there should be one.
No, there is one. Yeah. So
Obviously, I mean, if you add more layers, it will take a lot of time to,
Exactly.
converge.
Yeah, this in itself for one layer is taking a lot of time.
Correct.
Yeah, you can try this part with Keras. Absolutely. So, in fact, trying it with Keras or PyTorch or whichever of these libraries is a good idea, because this is a very sklearn has a lot of abstraction, but in Keras or even more than Keras, TensorFlow or PyTorch, you will get more liberty to play around with the layers, add more variations to it. So always a good idea to use Torch or TensorFlow or Keras in these cases.
okay. Parvati, were you able to install, or we can take that over
Take it
email?
offline. If anybody else has, then we can spend time. Otherwise, I can take it offline. Not an issue.
Okay. Anybody else? Else we are good. Yeah, I'll come. Okay, I think we should Thanks everyone. If possible, if you can switch on your videos, let's look at, let's at least greet each other through through seeing our faces. If possible, please turn on your videos, and I know it's late in the afternoon, but it'll be good to just okay, that's great. Anybody else? Okay, yeah, Basumatra, thanks. My greetings.
I think it'll take a minute, but everyone will turn on. So,
But thanks, Devanjana, for the great session.
yes.
We continue tomorrow with the unsupervised methods that Harshit will take over, and then we will have the industrial use case session where we'll look more closely to what Devanjana had started showing and I interrupted. So, so we'll look at Watson tools and all the great Watson capabilities that we have. So, okay, Parvati, any?
Yeah, no, I wanted to say it was a very good session. Thanks very much, Ranjana and and Devanjana. So this is really good, detailed view for beginners also, I would say. And the hands-on sessions are definitely going to be very, very helpful to pick up on building on more on that, right? So thank you.
Okay, thank you. Bye-bye.
Bye.
Hopefully to see you all tomorrow with the videos on again. Thank you. Bye.
Thanks, everybody.